Okay, so in this video we're going to talk about moments and what a moment is. The moment is a turning effect from a force, and we can calculate that turning effect, that moment, by using this equation. The moment is equal to the force times the distance from the pivot, and the units we're going to use are Newton meters, and force is measured in newtons and distance measured in meters. Now this turning effect from a force is going to act around a pivot, so in any situation that you look at you have to find the pivot. And in this situation, this would be the size of the force, and this distance here would be the distance from the pivot, because it's the distance between the pivot and the force. So we could use this equation above to work out the moment from this force here, and we can do that now. Let's do it in blue. So the moment is the force of 10 newtons times the distance of 2 meters. So the moment is 20 Newton meters. Okay? Now the next thing we can do is look at situations involving different moments acting on one system. So here we've got a seesaw and it's balanced on this pivot here, and I've got a force acting here and a force acting here. Now I can work out the moment from this force and the moment from this force and work out what's going to happen to the seesaw. Is it going to turn in a particular direction, or is it going to be balanced? So let's have a look at that. So what I've done here is, first of all, I've calculated the clockwise moment that's going around in a clockwise direction from this force, and I did that using my moment equals force times distance calculation. I've got a force of 3 newtons times a distance from the pivot of 2 meters, which gives me a moment of 6 newton meters. Then I have to work out the moment from this other force over here. This is a force of 4 newtons, and it's a distance of 1.5 meters from the pivot. And it's turning the seesaw in the opposite direction. It's turning it in an anti-clockwise direction, round like this. And if we do 4 times 1.5, we get a moment of 6 newton meters. So in this situation, I've got a clockwise moment of 6 newton meters, and I've got an anti-clockwise moment of 6 newton meters. If the anti-clockwise moment equals the clockwise moment, the seesaw or the system is balanced and it will not turn. So that's the case in this situation here. The seesaw is balanced because the anti-clockwise moment equals the clockwise moment. Now that is essentially all there is to moments. The tricky bit arises because you have to apply this physics to lots of different situations. So let's do some practice questions. Okay, let's read through this practice question together. This is one of the revision questions on the physics revision website. So you could have a look at this one and then do a different one by yourself if it's all making sense. So the diagram shows a lever, a weight is near the end of the lever, a force F pushes up on the pad and balances the lever. So because it's balanced, we already know that the anti-clockwise moments equals the clockwise moments. So it's really important to be highlighting and underlining important words in the question because they tell us lots about how to find the answer. So if we have a look at this diagram here, first thing to do is find the pivot. Here it is, so it's pivoting from there. So this is the lever and it's got 2 different forces acting on it. This one going down, which is going to create an anti-clockwise moment, and this one going up, which is going to create a clockwise moment. I've got my 2 distances here and I know this force. So then it says a 50 newton weight is pulling the lever anti-clockwise, that's this one, around the pivot. Calculate the moment of the 50 newton weight around the pivot. Give the units. So I'm going to write out my equation. Moment equals force times distance. Because I've got 2 marks here for this question, I always want to write out the equation. So that's going to equal 50 newtons. And then I have to look at the distance of that force from the pivot. So here's the force, there's the distance, and there's the pivot. So it's 20 centimetres. I need to change that into metres though, because they want or they've said that you can just choose your unit. So if you don't want to convert it, you could, but we'll be good and we'll convert it. So 20 centimetres equals 0.2 metres. So 50 newtons times 0.2 metres, and that is going to equal 10 Newton metres. If you use 20 centimetres instead, you could have 50 newtons times 20 centimetres equals 1000 Newton centimetres. And that would get you the correct answer as well. But probably best to get into good habits and keep working in metres rather than centimetres. Right, so the next part of the question, part B, the force F is just big enough to keep the lever balanced. What is the moment of the force F about the pivot? Now, because we know from this word here, balanced, that the anti-clockwise moment equals the clockwise moment, if this is the anti-clockwise moment, the clockwise moment must be the same size. So we're just going to write 10 Newton metres. And then it says, what is the size of force F? So what we're going to do here is we're going to say the force is equal to the moment divided by the distance from the pivot. So we rearrange that moment equation, and now we're going to put some numbers in. So we're going to have 10 Newton metres, and then we've got to divide it by a distance. The distance up here is 5 centimetres. So we've got to change that into metres because we're working in metres here. So that's going to be 0.05 metres. And that is going to equal 200 newtons. Now, if we have a little think about that and whether that makes sense, we know that the bigger the distance, the smaller a force we need to produce the same moment. So if we've got 20 centimetres and we've got a force of 50 newtons, to balance that out over a distance of 5 centimetres, we would need a much bigger force. So that does make sense. Right, and then here we've got the next part of the question. The force F becomes smaller. How should the 50 Newton weight be moved to keep the lever arm horizontal? So if this force becomes smaller, what's going to happen to the moment? The moment will become smaller. Let's write out our equation to remind us. So moment equals force times distance from the pivot. So if the force becomes smaller, the moment will become smaller. So what should we do to the 50 Newton weight? How should it be moved to keep the arm horizontal? Should it be moved further away, or should it be more closer? Well, we don't need it to provide such a big moment anymore to keep the arm balanced. So it should be moved closer. So we're going to be really specific with how we write our answer. We're going to move it closer to the pivot, because if we decrease the distance, the moment will decrease to balance out this smaller moment from here. Next question. The size of force F on the pad is 100 newtons. The area of the pad is 2 centimetres squared. Calculate the pressure of the force on this pad. So here we have to use a little bit of the work we've done in pressure. So we know that pressure equals force divided by area. The force is 100 newtons. Now we can leave this in centimetres squared if you want. Divided by 2 centimetres squared. But remember, our answer is going to be in newtons per centimetre squared. Let's make that really clear there. And we're going to get 50. So I hope that's helped. Have a go at some of the other practice questions on the revision website, and then email if you have any questions.